Hello, my name is Dr. Tamie Jovanelly, and I'm excited to be here with you to talk about tsunamis. But before we do that, we are going to return to our discussion on earthquakes. So what we said about earthquakes is that earthquakes are generated along a fault boundary. And so we identified some terms. The first is a lateral fault or a strike-slip fault. And we used the San Andreas fault as an example of that. We talked about a reverse fault where the hanging wall moves up relative to the footwall. And then we also talked about normal faults where the hanging wall moves down relative to the footwall. So these are three different scenarios where you can have earthquakes. And earthquakes are defined by the focus of the earthquake that's some distance below the surface. And it is at that focus where waves radiate out. So we can classify those groupings of waves into P waves, primary waves, S waves, secondary waves, or body waves. And it is the intensity of motion and stored energy from those waves that results in the magnitude of the event. And so your magnitude is defined by your Richter scale. And the equation for that Richter scale is magnitude equals log to the base of 10 times the amplitude. And we can measure, again, that amplitude on the Richter scale, which is linked directly to the intensity of the waves and waves movement. So we use those things to describe tsunami events. And I wanted to describe the mechanics of the tsunami event, but then I also want to give you a few case studies that have been really interesting and important to my research, just to give you some ideas of the impact of tsunamis around the world. So we are going to define a tsunami, and we're defining it based on it being a series of waves that is first and foremost generated by an earthquake event. And the earthquake event has to be a magnitude of 7 or greater. And additionally, the focus of the earthquake has to happen under the water. So relating this back to our plate tectonic diagram, you're thinking in terms of the Pacific rim of fire, so that intense convergent plate boundary that we see around the entirety of the Pacific Ocean is a great location to generate earthquakes. So you have the oceanic plate that's subducting, right, because it has a greater density. It's basalt, so it has a density of 3.3 grams per cubic centimeter, and then it collides with continental crust, and the continental crust is lighter. So that subducting plate that's underneath the water in the Pacific Rim of Fire can generate earthquakes. And we can see that throughout the globe. Earthquakes can also happen in places like Seattle, Washington, in the Puget Sound. So there's a major fault that goes through Seattle, and there's a major fault that goes through the city of Tacoma. Now, both of those are faults that are not on the coast, but because you have a large body of water called the Puget Sound, and you can have tsunami events that occur there too. So it's not always thinking in terms of the coastline, but you have some anomalies where you can have tsunamis happen inland. Also, you can have these tsunami waves happen in places where you get large landslides, volcanic eruptions, and of course meteorite impact. So the idea is that you have enough energy to generate a wave. When we talk about the meteorite impact, we're mostly thinking in terms of the meteorite that occurred 66 million years ago that killed the dinosaurs. So you had a big meteorite slam into the Yucatan Peninsula to form a crater about 9 miles in diameter, and it produced a wave that went onto land. So you can find that tsunami wave in places like Alabama or Mississippi. So when we talk about a tsunami wave, we are talking not about one wave, but we're talking about a series of waves. So we use the term wave train in geology to describe a tsunami. And what a wave train is, when you have an eruption along a fault, a brittle eruption along a fault, you have energy that's released. And that energy is pushing forward the body of water that's resting on top of it. So instead of getting just one wave, follow behind it, you're going to get 2 and 3 waves following it. So when we talk about a wave train, it is not just one, it's two and three. Usually the second wave is bigger than the first wave, and then by the third wave, the energy starts to dissipate. So it's called a wave train. And I think that's a big misnomer about tsunamis, and certainly necessary education, because one of the big reasons why there's fatalities with earthquakes is with tsunami events is because once a tsunami wave happens, people will want to run down to the beach to start their rescue efforts, of course, because people are in terrible situations. But little do they know that the second wave is coming and it's going to be bigger. The distance between the waves depends on how close you are to the epicenter of the earthquake. So it could just be a few minutes before the second wave arrives, or it could be 20 minutes. So there's tsunami warning systems now in place to help with that. When we make some comparisons between tsunami waves and wind-generated waves, there are quite a few. So tsunamis that are generated in the deep ocean have a really long wavelength. So their wavelength could be up to a mile long. And so you got this really long wavelength, but you have a really short amplitude. So similar to when we define the structure of a seismic wave, where you have wave length and you have wave height. So we're thinking in terms of that, applying it to a tsunami wave. So tsunamis generated in the deep ocean have a really long wavelength, could be more than a mile, but a really short wave height, could be just a couple centimeters. But as this tsunami wave is coming into land, there's a transfer of energy. So you move from wavelength to wave height. So that's one of the characteristics of a tsunami, is that it's got a really tall wave coming into land as it's approaching. And so also what's happening is the tsunami wave that's traveling at a rate about 500 miles per hour. Get your mind around that. So the tsunami wave is 1 mile long. It's moving towards the coast at about 500 miles an hour. And as it's moving towards our coastline, the water depth is getting shallower and shallower. And as that's happening, that's when you get the transfer of energy from wave length to wave height. So tsunami waves coming into land can be sometimes even more than 100 feet tall. And so it's a devastating wall of water that approaches the coastline. And again, like the wave height is going to depend on how close you are to the epicenter of the earthquake. And remembering, because these travel as waves too, right, they radiate away from the epicenter. So they radiate in all different directions. Additionally, when we talk about the difference between a tsunami wave and a wind-generated waves are dependent upon the fetch of an area. So the fetch is the area of which the wind is blowing across and having to do with the depth of the water. So as an example, if we compare the waves on the East Coast to the waves that on the West Coast, so Atlantic Ocean versus Pacific Ocean, the Pacific Ocean is going to have much larger waves because the water is much deeper and the Pacific Ocean is much greater. So there's more wind, more area for the wind to blow. So you're comparing the difference between 10-foot waves in the Pacific to really 4 to 5 maybe on the Atlantic Ocean. And of course, we're just considering normal wave systems. We're not considering like hurricane type system, just on the reg. We can also think about the limitations of fetch when we can consider a lake system. So remember, I'm from Detroit, so that's real close to Lake Erie here. If you can see that. I just brought out the map, right? Okay. I think that's really funny. Anyway, Lake Erie has a distance across which the wind blows, right? And so there is a limited depth in a limited area. So on Lake Erie, even in the worst storms, you're only going to get a wave height of about 2 to 3 feet. So there's limitations to systems that are generated by wind or tide. This gives you a little bit better picture of the shift in energy and the shape of a coastline. So this is showing you essentially a passive margin instead of an active margin. So you're looking at the continental shelf, the break, the slope, and then the deep abyss. So you're imagining a wave coming in, and as it's coming in and it hits the continental break, again, you shift from wavelength to wave height, and then it meets the shore. And as it's doing that, it's bringing in all the sediment that it's carrying with it. So essentially that wave that's moving at 500 miles an hour has a whole lot of energy. And because it has a lot of energy, it's scouring the basement of the ocean. So when you look at pictures of tsunamis, the water looks really super saturated with sediment, and it is. But that's good for geologists like me, because once that tsunami wave meets the shore and breaks, all that sediment will eventually have to dissipate out of the water itself, and that's what settles onto the surface to become part of the geologic record. So we call that a tsunami deposit, and we can trace those. So one of the tsunami deposits that I looked at was in Puget Sound, answering the question, can the Puget Sound have an inland tsunami? And the answer ended up being yes, because we could find that paleo signature along the stratigraphy of the Puget Sound. Another thing about tsunami events, that when these happen, you're imagining the energy that's being released along the focus of that earthquake. But when that happens, because you have such an amount of water on top of the fault system, you can end up having a drawdown. It doesn't always happen. It usually happens, and you can usually only see the signatures if the focus of the earthquake is close to a body of land. So you see this commonly in Indonesia. So when you have your earthquake activity, you have movement along your fault, and with that movement along the fault, you can end up with a kind of like a suction. And so when that happens, you have the drawdown of the ocean that exposes a beach face, and it happens very quickly. So if you watch videos about the Indonesian 2006 tsunami that happened on December 26th, you see people in Sri Lanka and Thailand, and they're like, what's happening to the beach? The beach is being exposed. This has never happened before. Is it tide? Is it low tide? But it happens so quickly, and you get so much beach face exposed. We're talking the tune of like a mile to 2 miles. If you watch the videos, you can see the boats that are ported end up getting dry docked because all of a sudden the water is gone. And that is a big indicator for a tsunami that's moving forward. So you end up with a drawdown, and that is just adding to the wave height that's going to be rolling in at 500 miles an hour towards the beach face. And so I give you a picture here. The picture on the top at Kaltura Beach in Sri Lanka is what it looks like when they're like a normal time, and then the picture below is with the drawdown. So you start to see the wave receding and moving outward. And I just want to show you a few slides about that Indonesia 2006 event that happened. It was not 2006. It was 2005. So I correct myself, December 25th, 2005. And when this event happened, there was a big earthquake off of the coast of Sumatra. And you can see that it's kind of on the northern coast. And when we're talking big, we're talking a magnitude 9 earthquake. And based on recurrence intervals, remember, it is not often for a magnitude 9 earthquake to happen. So you might get a magnitude 8 once or twice a year, like globally, and a magnitude 9 is even less than that. So this was a huge, intense earthquake. It's happening at a convergent plate boundary underneath the water. And when this happened, you can see where the wave radiated out if you look at the picture on the screen. So you can see the circle in the center. That's the origin of the tsunami, and then it moves away from that radially. So not only did the island of Sumatra get completely overrun by the tsunami, but you can see Thailand and you can see Sri Lanka. Sri Lanka is an island that's just off the coast of the eastern coast of India, and then you can see India. But the waves have can even move all the way throughout the Indian Ocean to affect places like Kenya and Tanzania and Somalia and Madagascar. So it is not just localized in one area, but it radiates out. It's going to take much longer to get to Tanzania and Kenya. It took about 4 to 5 hours to arrive. Remember that the tsunami waves, they're moving fast. They're moving 500 miles across the ocean. So it'll get there eventually. But when you're Sumatra, Thailand, or Sri Lanka, you had very little time. Mind you, a warning system was not in place. And so this marks the largest natural disaster on record in modern time. The largest natural disaster of modern time. And we call it that because 300,000 lives were lost during this tsunami event. 300,000 lives were lost, and quickly, so within 4 hours. And there wasn't a warning system that was in place during this time. It was kind of a place that was overlooked for tsunami events, although prior to this, even within that same month of December, there was a lot of tsunami warnings, a lot of energy, a lot of rumbling along Sumatra, where people were suspecting that there might be a major earthquake event that had happened. And this picture here just gives you a little bit of a before and after of what Sumatra looked like. Sumatra, again, was the closest location to the tsunami event, and the wave just completely ran over the island. Sumatra doesn't have a whole lot of high elevation, so the loss of lives was high, but it happened within minutes. And here's some images from Thailand. You can see the destruction of India too. There's been a lot of research since trying to focus on the trees that remained in place. So you can see that these palm trees, some of them remained in place, but you can see the overall destruction around them. And so the question is, well, why were these trees successful and other trees were not? Because in these areas, especially the poorer countries, you want to put infrastructure in place to help protect them from other natural disasters. And this planting trees would be something that would be relatively inexpensive to be able to do to act as barriers. So there's been a lot of science that goes into that. More recently, an event that happened about 10 years ago on March 11th was a pretty big and devastating earthquake that happened in Japan. So as we talked about when we focused on earthquakes, Japan, earthquakes are nothing new. It is completely surrounded by a convergent plate boundary. So there's a convergent plate boundary on the eastern coast, and then in the Sea of Japan on that backside, there's another convergent plate boundary. So the island essentially is completely surrounded by this convergent zone, and this convergent zone, especially on the Pacific side, has been really active. So it's nothing new to have earthquakes there, and they have really good building codes, especially in places like Tokyo, where there's 11 million people living, to help mitigate against destruction. But when tsunamis come into play, it just throws a completely different wild card, and that's what we saw with this event. So March 11th, 2011, there was an earthquake about 80 miles offshore of Sendai, Sendai is 109 miles northeast of Fukushima and 230 miles northeast of Tokyo. So when you have an earthquake, these cities are going to be felt too. And I give you an aerial photograph of Sendai before and after. And so when you look at the after picture, you can see the ponding of water miles and miles inland. And that's the thing about tsunamis. Like if it's in an area where it's a low-lying coastline, the tsunamis that are running at 500 miles an hour can go 5, 6, 7, even 10 miles completely inland. And that's the big challenge, because if they're going that far inland, there's not a whole lot that you can do to prevent the loss of life. If the coastline is steep, like the coast of Washington, for example, then the tsunami wave comes in and it runs into a cliff face and begins to slow down as a result. But in these situations where there's low-lying areas, it doesn't make so much of a barrier. There's no barriers. So Japan then is an ocean away from our west coast. And so even in this event, we saw on our California gauges a wave height of anywhere from 6 to 10 feet in the Pacific Ocean, like in a place like California. Fortunately enough, when the waves were coming towards our coastline, it was low tide. So it would have been another 5 feet taller had it happened during the high tide. But close to the event, the wave height in Sendai was about 33 feet tall, and you can see the inundation was about 5 miles, and it covered the infrastructure. Here I give you an example of the airport. And here's the wave coming in 20 hours after the earthquake event when it reaches the west coast. So the good news about this 2011 event is it allowed us to test the Pacific warning system. So the Pacific warning system went in place in 1964 after the Alaska earthquake event happened. So the Alaska earthquake event was a magnitude 9 and it sent a major wave to Washington, Oregon, and Northern California. And after this event happened, the community, the geoscience community, realized that tsunamis can happen on our west coast and that we needed to work with other Pacific Ocean countries to build a warning system. And how that works is that there's these buoys throughout the ocean, and if there's any like sudden and drastic change in elevation, then it puts out a warning. So anytime there's earthquake activity that's greater than a 7, the warning system will go off, and that's just to give people time to evacuate. So the further you away, like in the case of California, it took the tsunami wave 20 hours to get there. Pacific Ocean, it's a big place, so it gave the state of California time to evacuate their beaches. And if you look in that picture, like there's nobody in the beach because they've all been evacuated. Still, despite the warning system, this tsunami resulted in 20,000 casualties, and most of that was along Sendai. So at Sendai, there were, I showed you the picture that was completely overrun, the area that was completely overrun, and that's where the majority of the casualties were. And remember that Japan is pretty densely populated along its coastline. The bigger problem with this event is that, so first of all, you had a major earthquake event, and that's a problem. And so you have an earthquake event, and then this earthquake event triggered a tsunami event. So you have 2 natural disasters that are happening basically at the same time. And we mentioned how close the epicenter of the earthquake was to a location called Fukushima. And in Fukushima, there are nuclear reactors because Japan uses these nuclear reactors as a primary place for their energy. So how this goes is there's an earthquake. The earthquake triggers a warning system at Fukushima, and it relates itself onto generator activity. So there's a generator that's helping the nuclear reactors to produce energy. But the problem is that those generators, the backup system, was at a low elevation. So it was at sea level. And so now that the tsunami wave comes in, it takes out the generators that were in the basement, essentially, or at sea level. So that area gets completely flooded, and that leads to a nuclear meltdown of the reactors at Fukushima. And so it was obviously a devastating disaster that happened. And of course, they've changed the position of their backup systems, et cetera, et cetera. But it took a disaster in order for those things to become online. That's why it's so tricky to use nuclear energy in places that have natural disasters. It's very different than our nuclear reactors in Savannah at Plant Vogtle that are far enough inland that they're not going to undergo a hurricane. But as you have learned in geology, now our coastlines are not prone to earthquake activity because they're on a passive margin. So it's much easier to use nuclear energy where we are in the country as compared to someplace like California that is on a convergent plate boundary, and that's why it's not used there. So this disaster obviously prompted Japan to think a little bit different about the types of energy that they're using and to make some changes and some in hopes of preventing this from happening again. And so what they did is they built another seawall, although it's curious as to whether this seawall even helped. So the problem is that Sendai was so close to the epicenter of the earthquake that the wave height that was more than 33 feet tall just went over the seawall. And that made it worse because then the water couldn't retreat back to the ocean, and it really complicated evacuation. So we talked about Indonesia, and we talked about a recent tsunami event in Japan on March 11, 2011. And I wanted to highlight this event here because this has been a major part of my research. And so this is called the Kaido Nasaki Oki earthquake that happened on July 12, 1993. And I highlight this because this is an important earthquake and tsunami event that led to some pretty major changes in infrastructure. So in this instance, the earthquake is happening in the Sea of Japan. So instead of happening in the Pacific Ocean, it's happening in the back. You have the main island of Japan, and then you have the island of Hokkaido to the north. So there's a tiny island that's called Okshiri Island that's in the Sea of Japan and just off of Hokkaido. It's not very, very populated, but on July 12, 1993, there was a 7.8 earthquake in the Sea of Japan, and Okshiri Island was completely overrun by a tsunami in only 2 to 5 minutes. So it was really close to the epicenter of the earthquake. And the town of Enoni was completely destroyed. So I'll show you some pictures here. The picture on the right is after the tsunami had overrun the island. You can see the circle. So you can see the infrastructure that was in place before on the left and the devastation on the right. You also note that there's smoke. So when you have a tsunami that comes in, it usually breaks things like gas lines, and you can end up with like explosions and fires. And of course you get contamination and et cetera, et cetera. So that's why you end up with fires as a result of these tsunami events too. So it's a lose-lose situation for sure. But we're focusing on the town of Enoni here because this is where a fishing village was in place. And on this date, July 12th, this happens to be a national holiday for Japan. And so most of the women and children had left the island to go to Hokkaido to celebrate their little holiday. But who remained was the fellas that were fishing. So it's a big squid fishing industry off of Hokkaido. And this place of the Noni district, you can see it's flat, it's at sea level. And so July 12th in that afternoon, this is where the majority of the people were on the island. So the loss of life was really significant. And because they were so close to the epicenter of the earthquake, the wave height was probably more than 65 feet. And we can measure that in the field. So after there is a tsunami disaster, field scientists like myself, we show up and then we try to take measurements. And so we look for things like water lines. So just like with a flood, when you have an abundance of water, you can usually see that on trees or on buildings. And that's what what determines how tall the wave was in this case. So the about 12 miles of the coastline was completely impacted. Of course, other places were flooded, but the northern tip is a very low-lying area, as you can see, and there is some upper elevation on the island, especially towards the interior, because essentially it's like a little volcanic island. So interior wasn't so much affected as this portion, this southern tip. And you can see it's completely decimated. So here is on the island still today, there's a sign that marks the tallest portion of the wave at about 76 feet. And you can see that there's some elevation. So this event led to over 200 people being killed by drowning and fires. That's significant because the population in July 1983 was only 1,600. So a good portion of families were devastated by this event. And so when we focus on this, there was the Pacific warning system, but the problem was that they were too close to the event for it to even make an impact. And afterwards, when this tsunami was modeled, what they saw was, because it's in the Sea of Japan and you have a tsunami wave, it hits the western coast of Japan and refracts off, and you end up with this back and forth of a wave because it's trapped in the Sea of Japan. So it's different than a wave coming in and hitting the west coast of the United States, because it just hits the west coast. It doesn't refract and go back anywhere. But in the case of the Sea of Japan, it's kind of landlocked by two different masses. So that added to the complications of this event and made it worse. So then the question was, how is this island going to rebuild after this devastating event? And just like after many natural disasters that happen in coastal cities, the people want to go back. Like, this is where their livelihood is. So these people have lived on this island for generations upon generations. They have built their homes there. Their way of life is there. Like, many people fish for squid, as I mentioned. And so they want to come back. And so the people of Hokkaido wanted to help them to rebuild. And so the question again was, like, how are we going to do this? So the first thing that they did is, the low-lying areas that were overran by a tsunami, they decided to take all the debris that was carried inland and pile it up in those low-lying areas. And so they were able to rebuild areas like the Anoni district about 15 feet taller than sea level. So you've got 15 feet of elevation now above sea level. So that's the first thing that they did. Then when tsunami surveyors visited the island and looked at the devastation, one thing that they noticed particularly that was these tsunami waves like to move up areas of low elevation. So like they want to move up things like river systems. And there was a major river system that cross-cut the Anoni district, and that added a place of low resistance for the wave to move up. And when the wave moves up the river system, it's called a tidal bore, but it can flood areas adjacent to the river. So they decided to install a seismic gate, and that's what this picture is showing you of. And so when there is ground shaking of a magnitude 4 or greater that's instituted by the Japanese Geological Society, the gate closes. And so the gate closes so that it doesn't let water moving up and inland. The challenge is that this project was about $34 million in U.S. money. So it was pretty expensive. Next, so they built the Anoni district up about 15 feet. Now what they recognized was, well, the wave height was much taller than that, right? So we saw upwards of 76 feet. So they decided that they needed to build a platform to at least account for small incoming waves. And so they have, the Noni district is at sea level. They built 15 feet, and now they added a platform another 32 feet tall. And this was trying to allow for an evacuation route for people who are working at the harbor, which is the great majority of the population. So you see the platform over here to the right. So you're imagining there's a tsunami warning. You hear the warning that tells you to get to high ground. You run to this platform, and there's stairs that take you up to the top and up to shelters that are at even higher elevation. So this is the intention of this, is just to get you off of off the ground in a place for you to run to higher elevations. So you have you're almost about 50 feet at that point above sea level. And the next thing that they did was they put in a brand new seawall. And again, we kind of questioned the ideas of seawalls. We saw that in 2011, because the problem is that they trap water. But in this case, they put a seawall in that was 45 miles long. So remember, the major coastline that was hit was only 12 miles, but they decided to extend that for 45 miles, and they built the seawall another 50 feet tall. So hoping that even if there's a 65-foot wave, it's going to slow it down before it comes into the island. And so this is covering about 25% of the coastline of the Noni district. And they also put these things on the remainder of the coastline that are called dolos. So it's these concrete structures that look like jacks. They weigh about 2 tons each, but the effectiveness has always been questioned. So in the lower right-hand picture, if you look close, you can see these dolos that are kind of just thrown around like jacks. And that gives you an idea of the intensity and the energy of the water, right? So the water that's moving at 500 miles an hour has enough energy to pick up something that is 2 tons and just to throw around. The other challenge, of course, is what if you're around one of those? Now you've got this 2-ton structure in the water that is coming at you. And then they recognized that the good percentage of their population was elderly, and so they realized that they need to make handicap-friendly evacuation routes. And so in other areas that are of a lower elevation and that have more of the homestead population instead of the working population, that is that the harbor versus like the downtown area or the city center, that they needed to have other evacuation routes. And so this one, instead of having steps, it has a flat platform that's graded, so allow for wheelchairs, etc. It has a cap, so the idea is that it's strong enough to withhold water coming over top. It's lighted, there's alarm systems. And using systems like this, the platform and this type of evacuation route, they hold drills twice a year. And they put those in place, and they take it very seriously, allowing people to know where these systems are in place that allow them to get to higher ground. So as I mentioned, this event happened in 1993, and then 5 years later, they had all of these different systems in place. So the construction of these and the funding happened very, very quick. And I think that shows how much Japan has a respect for saving lives and putting infrastructure into place. So this total package cost about $1 billion to all this infrastructure costs about $1 billion to put in place, and the current population is around 1,900, and that has changed and fluctuated over time. In addition, because this is an area where they have had major tsunami events, there's also a memorial that they hold every year on July 13. I've been to this memorial, and this is a picture. They have a building with all the names of the people that were lost in the 2011 event. And every year, the governor of Hokkaido visits to pay his remembrance. So I show you these different things because it gives us ideas on how it is possible to not so much prevent tsunamis from happening, because we can't do that, but to put infrastructure into place for people that are living within these areas that can have devastation. And some of these infrastructures have been tried throughout other countries. The United States has not done this, although our evacuation routes are planned to get people to higher ground. It's challenging, I think, when you have so many people on a coastline to do that. So I'm going to leave you here today thinking about tsunamis and the intensity and their energy. And certainly if you're in an area where there are tsunami evacuation signs, I hope you take those very seriously, and that if you feel the ground shake, you should probably get to high ground. So I will leave you with that. Have a great day.